What specific problem does the string method aim to solve in the context of position encodings for transformers, particularly in the realm of robotics and vision tasks?
The string method aims to address the limitations of existing position encoding techniques, specifically absolute position encodings, APEs, and relative position encodings, RPEs, by providing a more general and efficient framework that maintains both separability and translational invariance. In the context of robotics and vision tasks, string enhances the representation of multidimensional token coordinates, which is crucial for tasks requiring accurate spatial awareness, such as open vocabulary object detection and robotic manipulation. By integrating string into vision transformers, VITs, the method demonstrates significant improvements in performance, particularly in scenarios where efficient 2D/3D token representation and sensible physical priors are essential. String's design allows for computational efficiency and adaptability, making it suitable for real-world applications in robotics, where the ability to generalize across varying sequence lengths and spatial configurations is critical. Overall, string provides a robust solution for improving the accuracy and efficiency of position encodings in transformer models used for complex robotics and vision tasks.
Can you explain how string works? Please illustrate the methodology step by step, including the mathematical components involved and how they relate to the properties of separability and translational invariance.
String, or separable translationally invariant position encodings, modifies queries and keys based on their respective positions to ensure that the dot products depend on the difference between their positions, R_I, R_J. The methodology begins with defining a mapping, RCDOT, that satisfies the translational invariance property RR_I_T RR_J equals RR_J R_I for all position vectors R_I and R_J. This mapping is expressed using the matrix exponential of a sum of skew-symmetric generators, L_K, which allows for the encoding of position information while maintaining separability, as each token's transformation is independent of others. Mathematically, string is represented as Z_I equals express left, sum_k equals 1_D_C, L_K R_I_K right, Z_I, where R_I_K denotes the kth coordinate of the position vector R_I. The use of matrix exponentials ensures that the transformations are smooth and differentiable, which is crucial for learning. The separability property is achieved because the transformation for each token is computed independently, allowing for efficient KV caching and compatibility with linear attention mechanisms. Overall, string generalizes the principles of rotary position encodings, RoPE, while enhancing computational efficiency and performance across various tasks, particularly in robotics and vision applications.
Could you provide a concrete example to demonstrate the inner workings of the string algorithm? Work through the essential steps of the algorithm using a hypothetical dataset or scenario to clarify its application.
To illustrate the string algorithm, consider a hypothetical scenario where we have a dataset of 3D object positions represented as tokens in a vision transformer, VIT model. Each token is associated with a 3D coordinate vector, R_I in R³. The string algorithm modifies the queries and keys based on their respective positions by applying a transformation defined as R_I, which is derived from the matrix exponential of skew-symmetric generators. For instance, if we have two tokens at positions R_1 equals 1, 2, 3, and R_2 equals 4, 5, 6, string computes the transformation R_1 and RR_2 to adjust the queries and keys accordingly. The essential steps involve first calculating the difference R_1, R_2 to determine the relative position, which string uses to ensure translational invariance. The algorithm then applies the learned transformations to the query and key vectors, resulting in modified vectors that reflect their spatial relationships. This process allows the attention mechanism to focus on the relevant context based on the positions of the tokens, enhancing the model's ability to generalize across varying spatial configurations. Finally, the output of the attention mechanism is computed, integrating the transformed queries and keys, which leads to improved performance in tasks such as object detection or robotic manipulation, as demonstrated in the experiments with Aloha and KUKA robots.
What are the main theoretical or practical advantages of adopting string over existing position encoding methods like RoPE and APE? How does string improve performance and efficiency in practice?
String offers several theoretical and practical advantages over existing position encoding methods like RoPE and APE. Theoretically, string generalizes RoPE by providing a unifying framework based on Lie groups, ensuring that it maintains both separability and translational invariance, which are crucial for effective token representation in various applications, particularly in robotics. Practically, string enhances performance by allowing for efficient computation through its parameterization, which reduces the time complexity to OND squared and space complexity to OND, making it suitable for large datasets and real-time applications. Additionally, string's ability to learn basis changes via a shared orthogonal matrix significantly boosts model performance, as evidenced by its superior results in object detection and robotic manipulation tasks compared to RoPE. Overall, string's design leads to faster convergence and improved accuracy across diverse tasks, showcasing its effectiveness in both theoretical and practical contexts.
How was string validated in the experiments presented in the paper? Could you detail the experimental design, datasets used, and the metrics for measuring the performance of string?
String was validated through a series of comprehensive experiments across various tasks, including image classification, open vocabulary object detection, and robotics manipulation. The experimental design involved comparing string against baseline models, specifically RoPE and standard APEs, using datasets such as ImageNet 2012, Places 365, and a 3D dataset derived from WebLI for contrastive learning. Performance metrics included accuracy for classification tasks, intersection over union, IOU, for object detection in both 2D and 3D settings, and mean success rates for robotic manipulation tasks in the Aloha simulation environment. Results indicated that string consistently outperformed its counterparts, achieving significant accuracy gains and demonstrating superior robustness in real-world scenarios, particularly in 3D tasks. The experiments also highlighted string's efficiency in learning and generalization across different environments and conditions, showcasing its practical applicability in robotics.
What specific outcomes were reported as a result of using string in the various tasks outlined in the paper? Please reference key performance metrics and improvements achieved compared to other methods.
The paper reports several specific outcomes from using string across various tasks, demonstrating its effectiveness compared to other methods. In image classification tasks on the ImageNet 2012 dataset, string achieved the top two models, providing the first absolute gains larger than 1% compared to regular vision transformers, VITs, with minimal additional parameters. For open vocabulary object detection in 2D, Kaylee string outperformed the baseline OWL-VIT model and RoPE variants, showcasing superior performance even in favorable conditions for RoPE. In 3D object detection, string variants provided significant improvements, with circulant string achieving A1, 5% relative improvement over the best RoPE variant. Finally, in robotic manipulation tasks using the Aloha simulation, string demonstrated the best success rate across 11 of 13 tasks, indicating its robustness and efficiency in real-world applications.